My name is Pedro Ferreira, and I'm going to talk to you about the project that I'm proposing to begin summer or autumn of 2021. You have my email here, and what I'm interested in is trying to find out if we can find new physics from looking at black hole mergers. A quick recap. We've now seen the gravitational waves from merging black holes. What I have here is the data from the first detection, which was a very high signal to noise event. And what you have is you have the in spiral, then the merger, and then the ring down over here. And we can use these, we now have lots of these, and we use these basically to learn about black holes. And typically what we're trying to learn about is what we learn about their masses and spins, which tell us something about where they came from, how they've evolved over time. What I'm interested in is using these measurements of mergers to learn about more. In other words, can we learn about new physics? What do I mean by new physics? New physics is this expression that we've used for many decades, and it really means new forces or new particles. We have this very good model of the universe. We have general relativity, we have the standard model. It predicts and it tells us exactly how things interact gravitationally through the strong, the weak, and the electromagnetic force. It works so well that it's been very difficult to find any exceptions to this. My idea is to use black hole mergers as a laboratory to look for evidence for new physics. We may not find anything, but we might as well look, given that it's so new. And an example is, if you think of general relativity, if you remember your GR course, you may not have learnt the action for general relativity, but general relativity is basically described in terms of an action, the Einstein-Hilbert action, where you have the Ricci scalar here, you have the metric here, and this gives you the Einstein field equations. But over the years, people have thought, well, is general relativity the correct theory? And one possibility, a very popular possibility, is that the Planck mass is dynamical. And so this thing here is actually a scalar field that goes in here that has its own kinetic term. And you can ask yourself, well, how different is this theory from this theory over here? And my proposal is to look for signatures of this theory, this scalar tensor theories. It's a very broad class of theories. In three places. I want to look at it in the ring down of black hole mergers. I'll explain what that is. In terms of clustering of the scalar field around black holes, and in terms of exotica that might be constructed in terms of the scalar field. So the first thing I want to talk about is when black holes merge. When black holes merge, they basically go through three phases. As I've said, they go through the in spiral, the merger, and the ring down. And the ring down is very well described. Well, the way to characterize is in terms of some special a combination of functions called quasi-normal modes. You've learned about normal modes in your first year maths, but quasi-normal modes are very special, and I could go. I don't have time to go into why they're special, but you can characterize them really well. And so the question is, can you find in the ring down evidence for the quasi-normal modes due to the scalar field? And I've got a plot here of the example. Here, over here on the left, I have what the ring down in a very idealized way looks like if you have your gravitational waves, and then you've got your new physics, your scalar field, which is circled here in over here. And what I'm doing here is let me change the color of the pen. I'm increasing the amplitude of that scalar field. And what I see is slowly it starts to distort the ring down. And so the question is, can we look for signatures of the scalar field in the ring down? Is there a way of looking for those signatures and then turning it around and using it to tell us what's distorting it, what kind of scalar field is distorting it? So that's in the ring down. Another example is these scalar fields that might exist, they can accrete around black holes and mergers. In other words, they can slowly condense around black holes. And the question, and this is a simulation done by one of my current graduate students who's simulating a Kerr black hole in this scalar field and watching how it accretes around. The question that I want to answer is, how can we model this accretion either numerically or analytically? And how can we measure its effect on everything else, on stars, on objects that are orbiting around these black holes? The last topic in this project is that these scalar fields themselves can collapse and form black holes. And there are many ways you can do this. I'm going to just throw some buzzwords at you. One of them is cosmic strings over here. The other is boson stars. Cosmic string base is basically a very it's a concentration of the scalar field in a line-like segment where it's very energetic along that line, but it lies on the vacuum outside. And the cosmic string loops, as they evolve, they oscillate and they'll collapse. And this is just a bad schematic of what happens. As the cosmic string loop collapses, at some point it might pass its event horizon and form a black hole. And as it does that, it's emitting all this radiation. And this radiation is going to be a combination of gravitational waves and the scalar field, which is coupled to the radiation. So how do we model these objects, cosmic strings or boson stars, as they collapse? And how do we find their gravitational wave signatures? So all in all, these are the topics that I would be looking at in a project on looking for new physics near black holes.